This derivative trick is using the reciprocal rule. Now, some calculus teachers will teach you the reciprocal rule. If they haven't, it's right here. It's the derivative of a reciprocal, meaning the derivative of 1 over a function. It's minus the derivative of that function over that function squared. It's actually a condensed quotient rule, and you can prove this to yourself by using the quotient rule. Now, while this is a nice trick in and of itself, it's very, very powerful when you're just dealing with 1 over x to a power, because this sort of derivative comes up time and time again. Let me show you what I mean. Let's take the derivative of 1 over x squared using the reciprocal rule. If I follow this, it will be a negative. F prime of x, well, the derivative of x squared is 2x, and that will be over f of x squared. If I square a square, that'll be to the 4th. Now I can reduce this. I can cancel one of these x's and get minus 2 over x cubed. And if you do this enough times, you'll see even a deeper pattern emerge that looks like this. And so here it is. This is the trick hidden within the reciprocal rule for functions 1 over x to a power. If I have 1 over x to the n, its derivative is simply minus n x to the n plus 1. Let's do a quick example using this super quick trick. Here I want to take the derivative of minus 4 over x cubed, and you might be saying, well, it's not 1 over x to a power, but the constants don't matter. Remember, with derivatives, constants just sort of stay along for the ride, so this negative 4 isn't going to affect our derivative trick. So what does the trick say? Well, it's minus, and here I'll keep the negative 4, this constant, 3, all over x to the n plus 1. So I'll just bump the power by 1. And so here's what happens, really. You're flipping the sign, and you're multiplying by the power of x, followed by adding 1 to the power of x. And it's very, very quick. It's a nice little thing that's going to come up a lot and save you a lot of time, because derivatives of a constant over x to a power happens all the time in calculus. So I hope you enjoyed this trick. Feel free to rewind if you want to see it again, and I'll see you in the next trick. This trick is for the quotient rule in very specific instances. Now, many people don't like the quotient rule. It's their least favorite derivative shortcut, and it'd be nice if we could save some time when we're doing the quotient rule. Now, this is one such trick, so let's look at it. It's the derivative of a quotient where a, b, c, and d are all constants, they're numbers, and these functions here match. Okay, so that's what's going to make this trick work. And you'll see what it is. It's the derivative of that function times ad minus bc all over c f of x plus d squared, all over the bottom squared. So it's still sort of like the quotient rule, but it's much faster if you're in these situations. And you'd be surprised how often this situation actually comes up. It seems like it might be a very specific instance, but you'll find many times where you can use this. Let's do an example. Here's an example where we can use the trick. And it doesn't look like it right off the bat, right? It's not quite in the form. Like, these are supposed to match. Well, in fact, they do if you simply rewrite it. If you rewrite it like so, in our trick, a is 3, b is 1, c is negative 1, and d is 4. And so I know what the derivative should be. I'll simply follow this formula. In this case, f of x is x squared, so I'll take the derivative, which is 2x, that's what goes right there, times ad, in this case 3 times 4, minus bc, so in this case that's 1 times negative 1, all over the bottom squared. And there's the derivative. How fast was that? So much faster than the quotient rule. You can clean it up if you like. 4 times 3 is 12, minus 1, that would be 13, times 2 is going to give me 26x, all over that bottom squared. You can write it back as the original if you like. And then there you're done. Much, much faster than the quotient rule. This trick is super helpful in the situations that you can apply it. So I hope you memorize this one. I hope you get something out of it, and I'll see you in the next video. This derivative trick is for taking derivatives of square root functions. Many, many times in calculus, you'll have to take the derivatives of functions inside of square roots, and it's time consuming. Many times what your teacher will suggest is to instead write the square root to the 1/2 power and then use the chain rule, and that's perfectly fine. But I've found that just memorizing this bit of information will make things much, much faster. So simply when we're taking the derivative of the square root, here just the square root of x, the derivative of the square root of x is 1/2 times the square root of x. And that's it. So this is a nice little thing to memorize that will save you about 2 steps when you're taking the derivative. It's just the derivative of a square root is 1/2 times that square root. Kind of has a ring to it. Don't forget to apply the chain rule. So let's instead take the derivative of this function, and it's a square root function. So what do? Well, the derivative is 1/2 times the square root. I just keep whatever's on the inside. And then by the chain rule, I need to times by the derivative of the inside. And if you like, since it's simply 1/, you can just write this on top. Let me show you what I mean. And so I just put the derivative of the inside on top, the derivative of x cubed being 3x squared using the power rule, and the derivative of 1 is 0. So this would be a complete answer. Notice how fast that was. Notice how memorizing this 1/2 times the square root saved us a lot of time. So give this a try when you're taking derivatives of your square root functions. This derivative trick is easily one of the most powerful derivative tricks I have ever seen. It's used for implicit differentiation, which is usually a long process. Many people don't like implicit differentiation. This lets you do it in one, if not maybe just 2 steps, but usually one step, one real step in implicit differentiation, and it makes it so much easier. This is really, really a great one. It's one of my favorites. Now, this is something that's not usually taught until Calc 3, and the reason is because it uses partial derivatives. But the idea of partial derivatives isn't too hard to get your head around. Now, here's the thing, word of warning. I wouldn't recommend doing this on a Calc 1 test or a Calc 2 test and just saying that's your answer, because your teacher, your instructor will want you to do it, quote, the long way, or the way that was taught in class, using the techniques in class. This trick is for checking your answers. And I will emphasize that again, if you are not in Calc 3, this trick is for checking your answers, making sure you're on the right track. So that being said, let's get into it. This is for partial derivatives. And let's say I want to take the derivative of this function. Okay, I want to take the derivative here using implicit differentiation. It would be a pain. We would have to do product rules and dy dx's or y primes. It would be a nightmare. But with this, it's in 2 steps or even just 1 step using this rule right here. Now, the first step is to move everything to one side so it's set equal to 0. That's already done. That's step 1. So this trick will just be a single step. So here, the derivative, or dy dx in this case, is going to be, if I follow my trick, it's minus, and it's going to be a fraction. Now this notation here, f sub little x, that means the partial derivatives with respect to x. A partial derivative with respect to x means y is a constant. Let me show you what I mean. What would the derivative of x squared y be with respect to x? Well, the derivative of x squared is 2x. And if y is a constant here, it just stays along for the ride. If this was x squared times 5, the derivative would be 2x times 5. The constants stay along. Basically, they just stay attached and you don't really have to do anything with it. What's the derivative here? with respect to x? Well, the derivative of e to the x is e to the x. And sine y, well, there's no x's in here, so sine y is simply a constant with respect to x. Now we have the numerator done. Let's do the same thing in the denominator, here taking the derivative with respect to y. Well, here, x squared is a constant with respect to y. It'll just stay. And the derivative of y is 1. Here, e to the x is a constant because it's with respect to y. So I'll just leave it. It stays along for the ride. And the derivative of sine y is cosine y. I don't even need to write times 1 here. And look at that, we're done. That's the entire derivative. That's the entire implicit differentiation. It's done in one shot. That's amazing. That's a real powerful trick, especially if you haven't seen it yet in Calc 3. Again, this is not enough work to get full credit on an exam. You definitely want to do this only to check your work. And what sometimes will happen with students is they'll get a little confused because sometimes this negative will be distributed in. You just want to make sure that algebraically this answer is equivalent to whatever you would get normally through your regular process, which you need to do anyway to get full points. But this is pretty amazing with partial derivatives, and I would recommend rewatching this video maybe a few times just so you get the idea of the partial derivatives. But give this one a try. See how you like it. I bet you're going to save a ton of time. Suppose I want to take the derivative of this nasty looking thing. It would be a real pain. You would have to use a quotient rule and chain rule and a product rule all in one single derivative. It would take you a lot of time. And so this derivative trick is going to make this much easier. The technique I'm going to use is called logarithmic differentiation. Now that is something that is taught in most calculus classes, but it's not always emphasized that you can use it in different situations. Usually, you use logarithmic differentiation when you have a variable in the exponent of a function. Here, that's not happening. We simply have a complex derivative. And let me show you how we can use logarithmic differentiation to make this much simpler. The process is this. I'll take the natural log of both sides of the equation. And if your problem doesn't have a y equals, you can simply just write y equals for yourself to remind you what's going on. Now, the reason I'm doing this is to take advantage of the properties of logarithms you would have learned in a pre-calculus class. So I'm going to do it a little bit quickly because I'm assuming that you're familiar with these properties of logarithms. And even if you're a little rusty, it won't take you too long to review them, or what I'm about to do might just click for you after seeing it again. So I'm going to expand this logarithm, remembering that if I have the log of a product, things in the numerator, I can write them as a sum. I can do log of this one plus log of this one. And when I have log of something in the denominator, I can subtract that one. So I'll subtract ln of this one. I'll also use the property that when there's exponents, I can write them out front. So this x had a 2, so I'd put that out front. This x minus 3 has a 4, I'll put that out front here. And now the derivative of both sides is very easy. Remembering how to take the derivatives of logarithms, we take the derivative of the inside, put it in the numerator, and the original in the denominator. So I have to take the derivative of both sides of this equation. The derivative of y is y prime over y, or you could use dy dx if you don't like y prime. The derivative of 2 ln x is 2 over x. The derivative of ln of x plus 1 is 1 over x plus 1, minus 4 over x minus 3. Again, this is just taking derivatives of the natural log function. If you're a little rusty on that, feel free to review it. At this point, y prime is the answer. That's the derivative. So I want to solve for that. I'll simply multiply both sides of this equation by y. So I'd multiply both sides by y, and you would be done, but it would be nice to end your answer with all x's. So what's y? Well, I know what y is. Y was the original function. So I'll just replace this y with the original that I wanted to take the derivative of. And there you go. There's the derivative of this nasty looking thing. And it wasn't too strenuous. We did this with much less effort than using the standard product rule, quotient rule, chain rule business than you normally would have. So feel free to look at this again. We just applied the rules of logarithmic differentiation. It made our lives much easier. So I hope you enjoyed this trick, and I'll see you in the next one. This trick is for taking derivatives of a product many times. Now here, this is 3 derivatives for the 3 primes of this product, and that would be kind of a pain because you'd have to do the product rule, and then on the next round you'd have to do 2 product rules, and then on the next round you'd have to do even more. It's going to be a mess. But with this trick, we can do it in more or less one line after we do some setup. Now, this is going to use what's called Pascal's triangle. If you haven't seen Pascal's triangle, it looks like this. You start with a 1 on top and 1's below, and then here's the pattern. Nothing plus 1 is 1. 1 plus 1 is 2. 1 plus nothing is 1. Nothing plus 1 is 1. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus nothing is 1. And you could keep going on this as long as you wanted. But here, we only need this 3rd row because it's for 3 derivatives. And so these numbers are the coefficients of the term. So our answer is going to look like 1 of something, 3 of something, 3 of something, and then plus 1 of something. And then here's how it works. We will take x cubed and just put it right here. On the next one, we'll take the derivative of x cubed. That would be 3x squared. For emphasis, I'll keep these together. The next one, I'll take the derivative again. That would be 6x. And on the last one, I'll take the derivative one more time to simply get 6. So for the first part of the product, I did derivative, derivative, derivative. And I'm going to do the same thing for the second term in reverse. So I'll start here. I'll simply just put the function down, and I'll go with the other way doing my 3 derivatives. So I'll do 1 derivatives, I'll do 2 derivatives, I'll do 3 derivatives. And this one was simple because it was e to the x. It's its own derivative. But would you look at that? We're done. That's it. No product rule necessary. We just needed the coefficients of Pascal's triangle. And to take this first function, place it in the first slot, and keep differentiating until the end. We take the second function, put it in the second slot, and differentiate the other way until the end. That's pretty crazy here. And of course, you could clean up the coefficients. I don't need times 1. I could do 3 times 3 is 9. But wow, that's a lot of saved time. This is a really nice one when you do some differential equations problems and you have to do these multiple derivatives of products. But this technique, I've almost never seen it taught. I don't think any calculus teacher will teach you this. So this is a really nice ace up your sleeve if you haven't seen this one before. Thanks for watching. In this derivative trick, I'm using the dy over dx notation to say the derivative of y with respect to x. And I'm saying that dx over dy is the derivative of x with respect to y. Now this equation looks true when you think about fractions, and it is true if these were fractions. These aren't actually fractions, these are differentials. Derivatives don't necessarily work the same way as fractions, but in many cases they do. And this is one of those nice cases where if I kind of just think of dy over dx as a fraction, this trick works out. In fact, this is a shortcut trick that I use for the derivative of an inverse function. That's its own theorem, but many people don't have it memorized, and this is a much simpler way to think about it, and I think a simpler way to use. It's very helpful when you forget what the derivative is of something that's a little bit harder to memorize, like inverse trig functions. Let me show you what I mean. y equals arctan x. Maybe you've seen this before, maybe you know what the derivative is, or maybe you have no idea. Here's how we can figure it out using this trick. Let's take the derivative of both sides. So I'll say that dy dx equals d dx of arctangent of x. In other words, take the derivative of arctangent. Well, by my trick, this is supposed to be the same as 1 over dx over dy. Well, what exactly does that mean? In other words, I don't want to take this derivative with respect to x. I want to solve for x and take the derivative with respect to y. Y equaling arctan of x is the same thing as x equals tangent of y. By definition, let's take the derivative of this. See, I know what the derivative of tangent of y is. It's secant squared of y. And that's what goes right here. So this whole thing should be 1 over, by my trick, and I'll replace the dx over dy with the derivative right here, secant squared of y. So this is the answer, but it's not very satisfying. Our answer should be in terms of x. So what is y? Y is arctangent of x. So this is actually secant squared of arctangent of x. Now, using some trigonometry, we can figure out what this is supposed to be. I'll think of this x as x over 1, and remembering that tangent is opposite over adjacent, using the Pythagorean theorem, the hypotenuse would be 1 plus x squared. And what's the secant of this triangle? Well, secant is hypotenuse over adjacent. So this will be 1 over square root of 1 plus x squared squared, or simply 1 over 1 plus x squared. That was a lot and kind of tricky, but it came down to this trick. Let's give it one more example. I'll give you a little easier an example so you can see what I'm doing. Let's take the derivative with respect to x of both sides here. This is much easier, but let's use our trick. Now it's the derivative of ln x. You should know what it is. It's 1 over x. Let's see how we get there. So dy over dx is d dx of ln of x. But by our trick, dy over dx is 1 over dx over dy. So in other words, I need to look at this original thing, solve for x, and take the derivative. Well, how do I solve for x? I'll simply exponentiate. That's how we get rid of that logarithm. So this would be e to the y equals x. And now I want to take the derivative of this with respect to y. Now I'm flipping the coin. I'm flipping the sides. So what's the derivative of e to the y? Well, it's e to the y if you're taking the derivative with respect to y. That's one that more people remember. So here, this will equal 1 over e to the y. And again, this is right, but we want our answer in terms of x's. So this is e to the what? It's e to the y. I know what y is. Y is right here. Y is ln of x. And e to the ln x, using properties of logarithms, those cancel out, and we simply get the 1 over x, which we know and are familiar with. So while I can't say that this is always a faster trick, it is a versatile trick. You can use it in different situations, and it can help you figure out derivatives that you're supposed to have memorized, but maybe you forgot. Maybe it's test time, and you need to know what the derivative of arctangent is, and you just don't know it. You can use this trick to figure it out. I hope you enjoyed this trick, and I hope you find some nice situations where you can apply it. I'll see you next time.